We can decide on which form of energy is present based on the scenario and what we observe. However, in any given scenario, different forms of energy can occur. Different forms can occur at any given moment, and they can transfer or change as the object makes its motion. Energy pie charts are a great way to visually represent which forms of energy are present, how they transform throughout the motion, and in what relative proportions they're present. Energy pie charts require us to write out the names of the forms of energy present. In order to make this task a little simpler, we write out the forms of energy in a shorthand, similar to how we wrote out the different forces in shorthand. Chemical energy can be represented by E sub Ch for chemical. Nuclear energy can be represented by E sub N for nuclear. Elastic energy can be represented by E sub El for elastic. Gravitational potential energy can be represented by E sub G for gravity. We can represent the kinetic forms of energy as well. Motion or kinetic energy is E sub K for kinetic. Radiant energy can be represented by E sub R for radiant. Thermal energy can be represented by E sub Th for thermal. Sound energy can be represented by E sub S for sound. Electrical energy can be represented by E sub E for electrical. Can an object have more than one form of energy? We already know about the law of conservation of energy. All of the energy remains the same amount, it just changes or transforms from one form to the next. As long as the total amount of energy remains constant, the energy can be spread among as many different forms as fits the scenario. Let's consider a basketball that's bouncing and look at 4 different stages in its motion. At the very beginning, so part A, it's off the ground, so we have gravitational energy. The only thing that's going on, it's not moving, so it doesn't have any kinetic energy, it's just been simply lifted off the ground. This is where all the energy is coming from, that stored potential energy. The next moment is as the ball falls to the ground. It's about halfway down to the ground. So now it's less off the ground, we can observe. That means it has gravitational energy. It has less than it began with, but it still has gravitational energy. But at this point, it's moving. It also has kinetic energy. If we ignore things like air resistance, we can start making assumptions about the ratios of energy. At this point, B is about halfway between A and the ground. So that means it has about half as much gravitational energy. So all the energy it started with, half of it's being stored as gravitational energy still, and half of it's been used for kinetic or motion energy. At point C, the ball is hitting the ground. It's being compressed. Whenever an object is stretched or compressed, we have elastic energy. So all that gravitational energy is trying to compress the ball down. When the ball hits the ground, it creates some friction because there's a collision there. So that creates thermal energy. You can hear the basketball bouncing, so that creates sound energy. The thermal energy and the sound energy in this case are not being used to help bounce the ball. Sound and thermal in this case are oftentimes lumped together as dissipated energy. This transformation of dissipated energy helps to explain why the ball does not bounce as high. Point D in the ball's motion represents right before it hits its highest point, so before it starts to fall down for the second bounce. We can observe that this ball is moving. If it's moving, we know it has kinetic or motion energy. It's off the ground, so whether it's been lifted or bounced up there, it has gravitational energy. That friction energy, or thermal energy in this case, and the sound energy, both still are represented. At each point in the motion, we have to look at how the total amount of energy is being used, or was being used. We're currently using the kinetic energy to move the ball. We're currently using the gravitational energy to store more energy so it can fall back down to the ground. The thermal energy and the sound energy were already utilized. This is why we refer to them as dissipated energy. We're not currently using that energy, but because the energy is conserved from each point in the motion, we need to account for it. This is why there's less kinetic and less gravitational. Having a better understanding for these dissipated energies, we can now answer the question, why doesn't the ball bounce as high each time? Many students would look at this and say, when the collision occurred, sound energy and thermal energy in the form of friction were given off, so energy was lost. The ball didn't have enough energy to bounce back up the second time. Energy is not lost. Energy is changing forms. That thermal energy and sound energy didn't disappear. They just kind of dissipated. That energy was still used. This is why we continue to represent it at point D, even though it was used and occurred at point C. We need to represent that conservation of energy. This is because at each of these points, the same amount of energy occurs. The energy is split different ways at each point in the motion. To help describe how it's split and the proportions between each of the different forms of energy at each point in the motion, we need a visual way to represent it. In this case, a pie chart. Each pie chart represents one whole. In this case, one whole represents the amount of energy. Because the energy remains constant as it's conserved and transforms from moment to moment in the motion, it needs to be represented as the same amount. We're just breaking it up into different forms. This is a two-step process for considering how to create the pie charts. Ask yourself, what forms of energy are present? Well, let's observe. We're holding the ball, about to let it go. It's off the ground, so it has gravitational potential energy. That's the only form. Now we need to ask ourselves, how much of each form? Well, there's only one form, so the entire pie chart has to be gravitational. It's all gravitational. 100% of point A represents gravitational energy. Let's look at point B. Follow the same steps. What forms of energy are present? Well, at this point, it's off the ground. Not quite as much off the ground, but it's off the ground. It's moving because it's falling towards the ground. Use your observations to determine which forms of energy. Once you know the forms of energy, you're going to determine the proportions. In this case, we're about halfway off the ground from where we started. So we can assume if there's half the amount of gravitational energy, that leaves half, the other half of the pie chart, for kinetic energy. If I know the proportion of one, I can assume the proportion of the others based on how much energy is there. At point C, we start by observing what we see and then determining which forms of energy are present. The ball is bouncing, so it's compressed, which means that most of the energy is turning into elastic energy. The friction caused by the collision creates thermal energy. The sound that's given off creates sound energy in the collision. Now that we know which forms are present, we can start to talk about how much of each form. At this point, we're making qualitative pie charts, so we just need to discuss how much relatively there is of each form. We can determine this by just observing the motion. Most of the energy goes into compressing the ball. I know this because it bounces. And it bounces not all the way up to where it started, but a good amount, most of the way up. The collision produces some heat and some sound. If I pick up a ball that just bounced, it's not going to burn my hand. And although I can hear the ball when it hits the ground, it's not giving off a huge amount of energy when it makes the sound. So that means that the majority of my energy has been transformed into elastic energy to compress the ball. A portion or a smaller amount has turned into sound, has turned into thermal. That wedge of sound and thermal represents why the ball doesn't bounce as high. Sound and thermal energy are oftentimes combined together to be one wedge called dissipated energy. As that wedge of dissipated energy gets bigger and bigger, the motion comes to a stop. A ball that's rolled across the ground comes to a stop eventually because of all the thermal energy and possibly sound energy given off. Eventually, it runs out of the energy that you provided it, and it comes to a stop. all of the energy has been dissipated. At point D, we look at what we observe. It's moving, it's mostly off the ground. We still have to account for that thermal energy and sound energy created by the collision. Now we need to look at how much of each form is present. The ball is almost at its highest point. We can observe at where it starts to turn back around. So that means we have mostly gravitational energy. We know at the top point of its height, it's going to stop, so it's going to have zero kinetic energy. So we're going to have low kinetic, high gravitational. The dissipated energy that we saw in moment C or point C is going to be the same amount. We're not continuing to have friction. We're not continuing to see sound. So the ball is not dissipating any more energy until the next collision. However, since this whole pie chart represents the total amount of energy, that energy needs to be represented. On the next bounce, ES and ETH are going to get bigger and bigger. Again, that's why they are oftentimes put together as just E dis, or E dissipated energy. Let's try a couple together. We have a cart that's launched using a spring. The cart then goes into a circular loop, and our final point is when it's at the highest point in the circular loop. Let's make observations about the initial point in this motion. The car is not moving. We know that because there's no lines behind it showing that it's moving. It's compressing a spring because it's about to be launched. It's not off the ground. So the only form of energy present is elastic energy. So 100% of my pie chart represents elastic energy. At the final position, the cart is moving. It's moving fast enough that it's staying in that loop, and it's off the ground. So we can assume that kinetic energy and gravitational energy are probably about the same proportion or the same amount. Because this cart is rolling around on the ground, it has kinetic energy, friction from the kinetic motion. It also may have sound as the wheels roll along the ground. Because we're not actively trying to create thermal energy or sound energy, we can lump these together into dissipated energy. So we have a small amount of dissipated energy, and then we have kinetic energy because it's moving, and gravitational energy because it's off the ground. Let's try example 2. Initially, the cart is in the same exact position. It's spring-loaded, it's not moving, it's not off the ground, so we start with 100% elastic energy. The final position, however, is not as high off the ground, it's still moving, and there's still been thermal energy given off through friction and sound energy given off through the wheels bouncing around. So we have some dissipated energy, the sound and thermal. We have gravitational energy because it is off the ground, and we have kinetic energy. We need to think logically and compare what we had in problem 1 to problem 2. In problem 1, we had about equal gravity, equal kinetic. In this case, there's less gravity. So we don't have more dissipated energy. We're going to actually have more kinetic energy. If we know that one amount of energy shrinks, one amount of energy somewhere has to grow. All of that energy goes someplace else. So in this case, it's moving faster. And if we think logically about what happens as an object moves in an upward motion, it slows down due to gravity. So the cart would actually be going faster when it's halfway up the loop than it would be at the top of the loop. So our observations about motion in the past help to explain why this energy is in the proportion that it is. Let's try one more. We have a load of bricks resting on a coiled spring, and then it's launched into the air. There's no friction or air resistance. This is another case where all of the energy is stored as elastic energy. It's not moving, it's not off the ground significantly other than the height of the spring. If you start to notice, many problems begin with one potential stored form of energy and then may end up releasing it into multiple forms. The final position is when the box of bricks has almost reached the height of its flight. So it hasn't come to a stop. We know that objects, as they move upward, slow down, stop, and then change direction and speed up on the way down. So this pile of bricks is moving, but it's not moving as fast as it was when it first started. That's because a lot more of that energy has transformed into gravitational potential energy. It took energy to get it up that high. So we have mostly gravitational potential and then some kinetic. At this point, these are just qualitative pie charts. So as long as it represents that you have mostly gravity and some kinetic, this will communicate the amounts of energy present in each system. On your own, try the last three problems, numbers 4, 5, and 6. Draw the initial and final motions and the energies represented at each point in this system.